wave pulse travels along a string with a speed that increases with the tension in the string and decreases with the density of the string. The wave speed is equal to the square root of the tension T divided by the mass per unit length mu. Increased tension leads to higher speeds, and increased string mass leads to slower speeds because of the extra inertia. When a string is fixed at both ends, it's possible to set up special resonant conditions in the string called standing waves. The lowest frequency of standing wave is called the fundamental mode and has a single antinode at the middle of the string. We label this mode as n equals 1 and note that the special condition for zero motion at the ends and maximal motion at the middle is when 1/2 wavelength occupies the entire length of the string. Thus, the fundamental wavelength is equal to twice the length of the string. Since frequency is equal to wave speed divided by wavelength, the fundamental frequency is equal to 1 over 2L times the square root of T over mu. The next resonant condition, called the second harmonic, has two antinodes and a single node at the center of the string. In this case, the length of the string is equivalent to the entire wavelength, so lambda 2 is equal to L. The frequency of the second harmonic is thus V over L, or 2 over 2L, times the square root of T over mu. Since this is twice the fundamental frequency, the second harmonic leads to a pitch that is 1 octave above the fundamental frequency. The third harmonic occurs when 3 1/2 wavelengths fit into the length of the string. Then the wavelength is 2/3 of the length, and the corresponding frequency will be 3 times the fundamental frequency. In general, the nth harmonic will have n antinodes and a frequency that is n times the fundamental frequency. The frequency of vibration of a string will thus be directly proportional to the harmonic number n, proportional to the square root of the tension in the string, inversely proportional to the square root of the mass per unit length, mu. It will also be inversely proportional to the length, L. In practice, you can increase the pitch of a vibrating string by increasing the tension, shortening the length, or exchanging the string for a lighter string. Although the frequency of a vibrating string depends on a number of variables, it's good scientific practice to only vary one parameter at a time. We begin by keeping the tension T, mass per unit length, mu, and length L fixed, and vary only the harmonic number n. Since the frequency is directly proportional to n, a plot of f versus n will yield a straight line with a slope given by 1 over 2L times the square root of T over mu. A function generator provides an oscillating current through the wire when attached to the two bare ends with alligator clips. A weight hanging over a pulley provides a known amount of tension, M times G, throughout the entire wire. The function generator allows us to vary the frequency as needed. A magnet straddles the wire with the north and south magnetic poles and provides an oscillating force to the wire with the same frequency as the oscillating current. When the standing wave resonance condition is met with the appropriate frequency, the wire will vibrate energetically. In the fundamental mode, we expect only one large antinode in the middle. Here the resonant frequency we measured to be approximately 11.5 Hertz. The frequency you measure, of course, will be slightly different, because you may have a different length of wire. You might even have a different mass per unit length. Make sure that the magnet is always placed near the middle of an antinode so that the wire is encouraged to move through large amplitudes there. When determining the frequency for n equals 2, the second harmonic, move the magnet so that it is approximately 1/4 of the length from one side. Then it will still be at an antinode. You may quickly find the approximate frequency for n equals 2 by doubling the fundamental frequency and then tuning in to maximize the resonance motion. Notice the two strong antinodes and single node in the middle. For n equals 3, the antinode is again at the center of the string, so move the magnet back to the middle. Triple the fundamental frequency and then tune carefully. Here we show the n equals 4 harmonic. We recorded the frequency for each harmonic number n. A plot of resonant frequency versus n yields a straight line with a slope given by 1 over 2L square root of t over mu. Your slope should be compared with this value, which also happens to be the fundamental frequency. The length of the string L is measured from the knot at one end of the wire to the point where the wire touches the pulley as a tangent. The mass per unit length has been measured by your lab TA and should be printed on the inside lid of the box of wires. The green wire will be approximately 0.005 kilograms per meter. Sticking with our principle of fixing all variables except one, we fix n, L, mu, and change only the tension. It's best to fix n at 3, since this is an easy mode to first locate the frequency and then to fine-tune. A plot of frequency versus the square root of tension should yield a straight line with a slope given by n over 2L times 1 over the square root of mu. Swap out the hanging weights for a variety of masses ranging from 100 grams to about 1.5 kilograms. Convert these masses into tension by multiplying m times g. In graphical analysis, you can create a new calculated column to obtain the square root of mass times 9.8. A plot of frequency versus square root of tension is linear, and the slope may be compared with theory. In the theoretical calculations, don't forget that n equals 3. Now suppose that n, t, and L are kept fixed, while the strings are swapped out for various string densities mu. Now a plot of f versus 1 over the square root of mu will yield a straight line with a slope of n over 2L times the square root of t. Choose several strings from a variety of string densities mu. Remember that the densities in kilograms per meter are printed inside the box lid. In graphical analysis, you may calculate a column defined as 1 over the square root of mu and fit a straight line. The theoretical value of the slope can be calculated from n, L, and the square root of t. I sincerely hope that you find this lab both enjoyable and instructive, since it might be just the last one that you're doing this semester.